So most of you have had to deal with users that complaining about the system is slow or it hangs or something like that. And obviously this kind of vague information is not helpful to you at all. However, we need to be able to quantify this kind of information. And the thing you also have to remember is that user response times, when you ask a user what the average response time is, they typically will respond with the 90 or 95th percentile in terms of what an average is. So they're thinking average, but the real numbers are 90 or 95%. So the database is often the first place to be blamed because it's kind of the centralized location, and it's people. There are so many other moving parts. It's easy to single out one part. So today we're going to talk about some of these issues and where to start, because many times people don't know where to begin. It can also be a very time-consuming analysis type of process if you haven't done it before. And it's one of those things where if you don't know where to begin, you're under the gun to deliver something, but you don't know quite where to look. So quite often people will look at the places that are most familiar. So DBAs need techniques for determining which components, servers, hardware, whatever, software, whatever, is causing the problem. What are the reasons for the poor performance? What's to blame? Is it an application that's not doing something right? Is it a disk that's not doing something right? Whatever. Or could it be software that's misbehaving and things like that? So basically what we're trying to do now is to figure out which query is the most troublesome, which hardware is the most troublesome, and kind of need something to direct our studies. So today is the first of several 30-minute presentations. We're going to discuss the pinpointing the sources of problems using PerfMon alone for today, but later on we'll delve into the more SQL Server-centric metrics and tools. And this is really important so that you don't waste time in a crisis looking in the wrong places. We will discuss some of the high-level things about the hardware, but we'll also talk about preliminary SQL analysis to see maybe there's something big going on that could affect everybody. The kinds of techniques we're going to be using will deal with SQL Server 2005 plus. So anything all the way up to 2014. It's also been recorded so that you can look at this at a later time or refer it to your colleagues. So you want to use measurements to determine whether or not the users are telling the truth, and if so, get a little more exactness to the kind of the complaints. I've had cases where people say, well, somewhere before 2 o'clock there was an error, and trying to figure it out exactly is very tough. So it helps, the more accurate the user information can be, the better off you'll be. Sometimes it's still very obvious when the problem occurred, but other times they're more subtle. So the idea here is that you want to capture all performance data you can on all servers that might be involved with the user experience. If the SAN is shared among servers, you want to collect on all servers that you can, because sometimes what happens on server X can affect server Y adversely. And then if the perceptions are valid, you know, when did it happen, how bad was it, how long did it last, and how do the users know it's bad? Do they, you know, is it response? Is the system just not coming back? Is it just slow? What is it? If the hardware is in trouble, then we need to figure out whether the application is making too many trips per transaction, or there are just too many transactions. Maybe we just have, the workload has outgrown the machine. That's not to say that the workload is inefficient. It's just a matter of we were doing too much, which is usually the result of business growth. So for today, we're going to talk about Windows Performance Monitor, PerfMon, and we'll try to figure out if we can see from PerfMon when problems occur, how long they last, which server, which components might be involved. Is SQL Server short of memory? Is Windows short of memory? You know, what's going on there, and use graphs to try to quickly figure out what's going on in should be noted that Microsoft emphasizes the fact that we should use PerfMon first before we jump right into the in-depth analyses of activity monitor or other kinds of things, because sometimes the problems are very easy to spot from PerfMon, and they are a little harder to deduce from, say, the VMVs or whatever, activity monitor, so on. So right now we're going to talk about processor memory, physical I/O, and SQL Server memory. We're going to expand on the PerfMon definitions because usually they're pretty vague. There's been a lot of work done with this work. I've done over 1,000 customer engagements and analyzed lots of data sets. So we have lots of experience in determining which things to look at. The user time, percent user time, is something you want to watch for on processor. People always ask me, well, which ones do I watch? There's so many metrics in PerfMon, I don't even know where to start. This is the short list. Basically, the top 4 processor, the next 3 are for every disk, and then you have available bytes, page life expectancy, and page reads, both for memory and SQL Server. They're separate metrics because SQL Server's memory work does not interact with the Windows memory work in terms of reads per second. So the percent idle time, the percent user time is how much time the system is being done by user work. Privilege time is processor overhead. Interrupt time and DPC time are involved in overhead handling for, say, disk IOs, network IOs, and software interrupts. The percent idle time is actually a utilization figure about how busy the disk is. Disk seconds per transfer per write are also a measure of how well or how poorly the disks are responding. The writes are useful because we can see if writes are different typical IOs. Available bytes, obviously if the system is out of memory, that's a problem. The same applies to SQL Server Buffer Manager. Page life expectancy is a very good measure of when the system has memory as far as SQL Server is concerned. The page reads per second is something to indicate how much data is coming off of disk, either into Windows memory or into SQL memory. So one of the things that people want to look at is percent processor time. That if it's consistently more than 70% overall, then you have a problem. You'll see this go up and down for individual processors. That's usually not a big deal. However, especially if you have queries that make on a few processors at a time and then go away. But if you see that your processor complex is greater than 70%, then an issue. Privilege time, greater than 30% for any processor. Again, these are sustained values. That indicates there's some over going on. The only exception to this is when you're doing a backup. You'll see a lot of privilege time when you're doing a Windows backup. Interrupt time and DPC time, those should be fairly low. And again, those should be something that you don't have to do very often. It's something that, again, it's usually a very efficient operation. So if you're doing lots and lots of this, it's slowing your system down a lot, and it could be a real problem. So you'd want to look into this. Maybe it's a bad driver. It could be a lot of things. Again, the only exceptions there are when the system is just being bombed by network packets. So if you have a very high transaction volume system, you're liable to see interrupt and DPC time, particularly DPC time, be very high, and that's a natural event. Percent idle time, it should be less than 40% for any disk LUN, particularly SQL LUNs. Disk seconds per transfer, you want 40 milliseconds. That's pessimistic. You generally want it to be around 15 or 20 if you can. You want to have available bytes, about a gig or less. Less than a gig, you start to run into trouble. And page life expectancy should be at least 300 seconds. The processor object, I talked a little bit about interrupts, but basically don't typically look at this. There's this user mode and kernel mode. Kernel mode means that it's Windows time. So basically you have the situation where the interrupt times indicate that the Windows overhead is occurring. So what you have to do is actually compute the difference between privilege as shown by Windows and subtract out the interrupt-related times of interrupt and DPC to get the true Windows time. And again, just to reiterate the fact that during backups, you will see these numbers be very high, and that's normal. If you see it at other times, then that's not normal. The system processor queue length is a waiting list. This is affected by application design. So if you have an application that goes to sleep and then wakes up every thread it's got, and then turns around and falls asleep and then does it over again, your processor queue is going to look really awful. In reality, it's not. Sometimes the application can affect it. You have to be careful and understand. I use this more as a relative measure than an absolute measure. And context switches, on the higher the number of processors you have, the more context switching you're going to have, particularly in high volume transaction systems. So to pictorially show you what's going on here, if you look at the graph, abnormal is showing you what is not commonly, and you can see here the interrupt is very high. In this case, I believe it was a bad driver. The normal stuff is more like what you want to see. You want to see the system being given to the user work, not to Windows overhead. Physical I/O measurements for SQL Server systems are critical because often SQL Server is I/O constrained. The I/O time is measured directly by the disk driver, which performs the actual work going to the drives. I/O time is kind of a disk time. It's service time, which is the working time, plus the queuing time. So it's both of them. So think of it, if you're in the post office and you're waiting in line, and then you get up to the person behind the desk. The person behind the desk is the service time. The time you spent in line is the queuing time. And what I/O time is measuring is the entire time you were in line, including the time you were at the counter. Queuing is not always the cause of large I/O times. It can be possible that if you're doing gigantic I/Os, it can actually create a lot of headaches for you. For example, if you're streaming a lot of data back from the database, doing read-aheads, 300-400K I/O types are not uncommon, at least as measured by PerfMon. So, in those cases, it takes a lot of hardware to make those things perform very well. The most frequently, physical measurements are unfortunately the most misunderstood metrics. They are reported for each physical disk, and the thing you have to remember is if it's hardware RAID, which most people use, whatever Windows sees as a LUN is what's going to be reported as a physical disk. So it may have 3, it may have 100 disk platters underneath it. So you have to be very careful to determine what it is that comprises a LUN. Using disk idle and disk transfer times to detect contention within a RAID itself is very useful. I alluded to this earlier by saying that you want to know when the RAID is the writes are worse than the reads, and that can often indicate that you're using RAID 5 and that it's not working very well. It also is, these numbers can be obtained for each logical disk, so sometimes you have a shared logical drive, a physical disk that has multiple partitions on it, and in that case, it'll show up for each one. To specify what's going on here, you have disk seconds per transfer. Again, it should be about 20 milliseconds if you can. The lower is better. Again, if your I/O sizes are huge, this may not be possible. Percent idle time. This is commonly ignored, and you have to be very careful of this. Once it reaches 0, you can't push any more through the system. basically, I think of it more as 100% minus idle time, which gives you an actual utilization. Management understands utilization better than idle. So I typically do it saying how busy something is. Disk transfers and disk bytes, these can be very helpful because you have to be able to know what's going on in your subsystem, and you have to be able to see when you've reached some kind of a cliff, which can occur even on solid-state disks. Because I've seen cases where once you get past 50 megabytes a second, the disk performs poorly. Below that, it can perform extremely well. Above that, no matter how much above, it can perform very poorly. So it's quite variable, and you have to be very careful of this. Logical disk, same counters, plus the space-related ones. It's, again, useful if you're sharing drives by a logical LUN. So this queue length includes the IOs in progress. So whereas the processor queue was a waiting list only, this one includes the IOs in progress. This one is used by most people to look at whether or not the disk is busy. The problem is that quite often it doesn't indicate when there's an issue. And people don't understand that it includes the IOs in progress. So you could have a queue depth of 14, but if you had a 14, 15, 16 drive LUN, then it may be just all the drives are working and nobody's really waiting. So queue length can be very misleading. It again assumes a relationship between among transfer times, utilizations, and queue lengths. I find it to be not very useful unless you're dealing with a VM guest on a very busy host, other than 50% processor utilization. At that point, numbers can get very skewed for utilizations. So you have to rely upon. I instead use transfer times and percent idle. Again, the interpretation is a little bit difficult because you have to know how many disks you really have underneath there, and particularly in today's world where a lot of things are put across SANs, that there really isn't a good limit on each one. You really know where everything is. There is no one-to-one correspondence in a lot of cases. So graph on number 16 shows that there are cases where utilization and queue depths match really well, cases where it doesn't match at all. So again, it's kind of a crapshoot as to whether or not it's going to work well for you. Some of the most misunderstood ones still are percent disk time, although you see it much less in narratives now than you used to. The PerfMon explanation implies it's the utilization. It's actually just 100 times the average queue length, and if you're looking at it through PerfMon, it's an artificially constrained number, so it's actually a useless number, but it's often referred to as busy time. In fact, I've seen it even Resource Monitor on Windows 2008. It shows as active time or something like that, which makes you wonder which one they're using. Again, actual busy is 100 minus percent idle. And again, once you get to 100, you can't push anything more through the LUN. So this is what you don't want your I/O subsystem to look like. The other drives are fine, but disk 06D is in terrible trouble most of the time. So in this case, you have a LUN that does not perform well, is being pushed to the limit. You're in those peaks, as you see in the background, that you cannot push any more work through that LUN. This is a similar kind of graph. You can see this is what you don't want your system to look like. In this case, it's two different ones. And you can see that the systems, the LUNs are very busy. You can also see in this case that you've got multiple LUNs on a physical LUN can create trouble, because this is where you'd need logical to figure out whether it's RRS or V causing the problem. On disk 2T, it's pretty easy because you know that's the only one. Again, these numbers can be, you have to look at the scale to be sure you're seeing this, but you can see 300 milliseconds per I/O or 250 is definitely not where you want to be. So this LUN RSV is having trouble. So if you look here, the utilization is very high. And if you look here, the performance is very poor. So between the two, you'd have to take this LUN and break it apart. That would probably be the simplest way to go here. Sometimes the traffic can be very useful, and this can see how all the LUNs are used at the same time. It's hard to say whether this is a problem or not, but it's something you definitely should know, that you're getting very even use to this. Most often you do this kind of behavior, you actually see very disparate kinds of behavior. The I/O performance counters are incomplete as they typically stand. You do not get service time per transfer or queuing time per transfer. So as I mentioned before, you have the full I/O time. In this case, we want to pull apart the service time and the queuing time. We can actually use something called the utilization law to figure this out. Simply stated, the utilization law is a function of the completion rate and the average time that it takes a service, the average service time for a given transaction. So in this case, it's not a perfect tool, but it's quite often very good. And certainly for our purposes, it's close enough. So what we do is first we restate the utilization law, where we compute the service time as the utilization divided by the throughput. And you can use either physical or logical disk for this. What I tried to do here is to make it very easy for you to use. And the italicized entries are PerfMon counters, and the blue entries are the calculated numbers. So you can see how the disk utilization is 100 minus percent idle time divided by 100. That creates a decimal. And then you have the service is the utilization divided by a second. And then the queuing time is the difference between the transfer time and the service time. So this gives you the ability to see if is all my time being, if I have 250 milliseconds for an I/O time, is it coming from queuing or is it coming from just I'm doing gigantic I/Os? So here are two examples of these calculations in action. You can see that in both cases, the service, in one case, the service time is 563 milliseconds, the other one's 25, but you can see that they're both having horrific amounts of response times, over 2 seconds. And the actual numbers from an actual system. So again, queuing was happening, but in one case, the I/Os were much bigger than the other. The problems began when a faster processor was put in and attached to an existing disk comp subsystem. And what happened is the customer blamed the new processor for performance, saying it was bad architecture and all this other stuff. It turns out that the processor was so much faster that it was swamping the disk subsystem, and they didn't know. So the solution to reconfigure the entire I/O subsystem and also to reconfigure the physical LUNs. Again, one thing you have to be very careful of when you do this, what I call cross-hatching kinds of things, where you have bits and pieces of LUNs spread out over a it's great in concept, but as soon as hotspots start to develop, it gets to be very difficult to extricate yourself from that situation, because you've got stuff scattered all over the place, and it's very difficult to unravel it. So some I/O counters from the database side are page reads per second and page writes per second, and this measures the physical I/Os done by SQL Server. SQL Trace and many other sources often measure logical I/Os. They may indicate a bad application, insufficient database memory, lack of indices, all kinds of things. So what I try to do is plot reads and writes on the same graph, and I particularly try to see if I have poor performance when I'm doing lots of writing. Sometimes it's helpful to do full scans and forwarded records per second to get a better view of what overall is happening. And here is an example of this kind of graph. You can see that it's, that the I/O spikes occur, and you also can see that sometimes we're doing full scans or we're doing forwarded records, which right now it's beyond the scope of this session, but it basically means a double fetch when you're trying to access data. So detecting insufficient SQL memory, you want to use page life expectancy. And basically what this says is how much time is a buffer that isn't locked into memory going to hang around. It's an aged number, and strangely enough, it drops extremely quickly and then will increase slowly. I'm not 100% sure why this behavior occurs, but it's a phenomenon I have noticed over and over again for many, many years. It's just the way it works. So basically, you'll see this number drop like crazy when there's a problem, and it'll slowly work its way back up. And this doesn't mean that you're very slowly getting your memory back. It's just that it's an aged number. So if you have below 300 seconds, you want to allocate more memory to SQL Server, or maybe optimize your queries so you're not doing sorts. And again, you want to avoid data churn because that can cause low page life expectancy because you basically read something in and throw it out and bring something in to replace it. A good indicator of this is page lookups per second. It's the number of times SQL Server tried to find something in the buffer pool. Whether it had to go to disk eventually or not, it doesn't matter. It's effectively a logical read. So the reason this is important is that it helps you determine whether you're looking for a bad query or a collective situation where all kinds of queries are causing trouble. In this case, you can see that we have a very bad situation, then we have a good situation, then we have a horrible. So what you want to do is be in the good range where you're above the 300 seconds, and you want to stay out of the part where you're below. Because if you're below in the bad or horrible phase, you're actually spending a lot of time churning and doing database overhead trying to get things to happen. The batch requests per second is kind of a number. It's actually the number of select, insert, and delete statements that are executed regardless of whether they came from a stored procedure or an ad hoc batch. Each of these statements triggers an event which increments the counter. So it does, again, it's a very good key volume indicator about how much traffic is flowing through your system. Now this is very helpful because you can figure out if the lookups you're doing are caused by a lot of small queries or a few large ones. And you can see the graph here where it shows you that in the first part you've got a lot of, they're about the same number of lookups, but in the first case we have a lot of small queries doing it. In the second case we have a few large queries. So if you go to tune the first part, you're looking for some smaller queries, just lots of them. And if you're going to the second part, you're looking for a few big queries, the offenders that packages most often reveal. So again, the key here is that the part 2, the large queries, are the ones that the packages we find. The ones that are harder to find are the ones where you have the collective effect problem. So in conclusion, PerfMon should always be used to focus the tuning efforts to make sure do we have a disk that's crazy, do we have a processor that's swamped, do we have too little memory in Windows, do you have too little memory in SQL, some of the bigger picture items. And then if you do, then you can delve, where to look once you get into the in-depth numbers from SQL Server, which we'll start to cover next time. It's extremely important to combine all servers because for example, I had a customer that had an Exchange server that when they did their maintenance on the Exchange server, because it shared disks with the SQL server, all of a sudden the SQL server's disk go times got enormously high. So as follow-up, again, this session recorded, so hopefully you can go back and listen to it again if you want. it to colleagues. Please attend the next session. It will discuss some of the dynamic management views that some of you are probably waiting to hear about. Please complete the 4-session evaluation to let us know how we can help you and what topics you'd like for us to cover in the future. And at that, I will end the webinar, and thank you very much for attending.